Okay, so 4.4 is permutations when objects are identical. And as we mentioned last section of 4.3, we talked about when they were distinguishable. So now we're going to find out what happens, how do we account for the fact that some objects might be identical, and how do we consider those arrangements. So, last section I think I did maybe give you something like this. If I was to take the letters in the word add, and I was to ask you how many different ways could you arrange them, and you told me that these were 2 different ways. And you look at those, and you know for a fact that one D is identical to the other D. They're both the same exact thing. And you said, well, Mr. Maxwell, what I did was I took the last D and I switched it with the one that's in the middle. I just switched those. So that's 2 different permutations. And another student might say, you know, that guy's crazy because this is the exact same word, and so therefore it's not a different permutation. So this is the case where these are not 2 different permutations. This is the same permutation, okay? Because the D's are identical, or they should be if I wrote them totally identical. You know, they're the same letter. So when objects are identical in a set, it makes sense that maybe there are fewer permutations, right? There are fewer arrangements, okay? And which is totally true. Now we could do this, dad or D, D, A, right? But, okay, so those are 3 different ones. Do we have any others? Do we have any other arrangements there? No, not really, right? So we only have, looks like we only have 3, okay? Because the A is in front, the A is in the middle, and the A is in the end. And the D's are identical. So if that was 3 different letters, we would have more, right? We'd have 6 arrangements. But here it looks like we only have 3. So how do we account for that? It's not always half. I know 6 and 3, that's 3 is half of 6, but it's not always half. If you look in your textbook, here, here's another example with different plates, okay? So we have different colored plates. Here's a blue one, here's kind of a yellowish one, green, red, and then we have 3 white plates. Now it would make sense if these plates are identical, that if you switch the order of these 3 plates, you still would have the exact same arrangement, right? So we're going to have fewer permutations when we have some identical objects. And that's just another way to think about that. There's the word add, and then there's a stack of plates, okay? So if you look down here, all right, what they're going to talk about is, look at this right down here. You see this? Now this right here gives us an indication of how to reduce the number of permutations when accounting for identical objects, okay? So we're not going to work through this example per se, but we are going to notice that we have, you know, this show up again. And notice that we are dividing now by certain factorials, okay? So if we want to reduce the number of permutations, we are going to have to divide by certain factorials. And I'll get you just to skip ahead because to page 266, okay? And we look at the in summary already here. Boy, we're going through this lesson pretty quick, eh? But it says here there are fewer permutations when some of the objects in the set are identical compared to when all the objects are different. Now that makes sense. This is because some of the arrangements would be identical even though those identical items have been switched. So this is how we account for the identical arrangements, okay? So this right here, I'm going to get you to copy this down. Permutations, and this is when some things are identical. So we have P equals, we do always start off with the total number of items, and then a factorial, okay? So we count all of the items, even the ones that repeat, okay? We start off with that on the top. And then what we do is to account for the things that repeat. Now look at what this says. It says where A are identical, so the number of certain things here are identical, and we have some other things that are identical, and even yet more, if we have third a group of things that are identical, and so on, this is how we account. So if you got this written down, so let's put this into action. Okay, just going to bring this over into the notes. Oh, with my cursor there, that's no good. Okay, anyways. So if we have this as a formula, let's take a look at this word, add, ADD. Okay, so the number of permutations for identical with some identical objects are going to be 3 factorial, because that's the total number of letters that we have. And we have 2 identical D's. Okay, so let's say that the D's are the first grouping here, and we only have one group that has identical objects. So, and how many do we have? Well, if we go back to the notes there, okay, it says, for example, if we have 2 A's, see that's 2 A's there? So that's a 2 factorial. If we have 2 B's, that's another 2 factorial. So what do we do in this case? Well, we have 2 D's, so we divide by 2 factorial. So this right here is because there are 2 D's. And it's pretty much as simple as that. So if we evaluate this, that's 3 times 2 times 1 divided by 2 times 1. And of course, you can do that in your calculator if you need to, but look at that. It just ends up to be 3, which that's exactly what we wrote out there. Okay? We'll do some more examples, but do you have any questions about this so far? Okay, this accounts for anything. And we'll do some more examples with words, okay? All right. Let's see. What do we have? Oh, why don't we talk about the word Canada? That's always fun. Yeah, go Canada. Okay, so Canada. So the question is, how many permutations do we have for the word Canada? And what you notice is that we have, first thing you want to notice is you count all the letters, 4, 5, 6, so there's 6 letters. So the number of permutations is going to be 6 factorial. We know that's going to be part of it. If they were all distinguishable, all different, that's our answer, right? We evaluate that and we're done. But because we have a group of letters that are identical, we now have to divide, because we need to reduce the number of permutations, so we're going to divide by what? What am I going to put in the bottom here? 3 factorial. Good. Why 3 factorial? You're exactly right. Can you just tell us why? Because there's 3 identical A's. Very good. That's it. Okay? So what's 6 factorial divided by 3 factorial? Well, that's going to be 6 times 5 times 4. Right? Because the 3 factorials are going to cancel out. So you could probably do this in your head. 6 times 5 is 30 times 4 is 120. Okay? So does that sound right? Okay? What about another one? Let's do another one. What about this one? Good old Saskatoon. It's my favorite berry. And it's one of my favorite cities. I went to university in Saskatoon at the U of S, and it was a fantastic experience. Although I live in Regina now, I'm not supposed to say that I like Saskatoon. Yeah, well, kind of a bit of a rivalry. Moose Jaw too. No, I'm not supposed to like Moose Jaw. Although I was born in Moose Jaw, I played hockey in Moose Jaw. I actually really like Moose Jaw too. Yeah. Anyways, that's an aside note. Okay, so let's find out how many perms we have in Saskatoon. We could just walk down the street and see how many people have curly hair. We could do that, or we could. Okay, too early. Good. We could look at the number of letters that we have. How many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial. Now, what about groupings of identical letters? Well, I see two S's here. So guess what? 2 factorial. Am I done? No. I see two A's here. So another 2 factorial goes down there. Am I done? No. I see two O's staring at me. Okay? So, I know, creepy. Just trying to wake you guys up. Do you guys know? You're not noticing that? Okay. It's like Oscar the Grouch looks like or something. You remember, you guys ever watch Sesame Street? No, why would you? Okay. You guys are in grade 12. Alright. Any more? What about K's? Nope. There's only one T, only one N. We're good to go? Okay, so there you go. Now, how do you evaluate this? Well, I mean, you could write it out. If you have brackets on your calculator, brackets are awesome on the calculator, so you can do that if you want. Let's see. So you could do 9. Oh my goodness. Factorial is tough to get to in this calculator. 9 factorial divided by, and then you could use brackets, right? What's 2 factorial though? It's 2 times 1, right? So just 2. You don't even need to do this on your calculator probably. But 2 times 2 times 2 is 8. But I'll just do 2 times 2 times 2. Okay? This is how you would set it up in your calculator. Make sure you use brackets, okay? Because if you don't use brackets here, it's going to do 9 factorial divided by 2, and then it's going to do that calculation first, and then multiply that by 2, and then multiply it by 2. But we want the 2's in the denominator. Okay? So, do you get a big, huge number like this? 45,360? Yeah? Okay. That's a pretty big number. Did we do something wrong? Or is it possible that we could actually have that many different arrangements? What do you think? Yeah? Yeah. No, I think we did everything right here, guys. So this is good. This is a lot of different arrangements, but even with identical letters, you know, 45,000 different ways. Isn't that crazy? That's not so, isn't it? Absolutely not so. Well, you think about it. The two S's could be in different spots. That's 1 and 3. It could be 1 and 2. It could be 1 and 4, 1 and 5, 1 and 6, 1 and 7, 1 and 8, 1 and 9. Right? That's no problem. And you know, if you keep doing that, even though they're identical, we still got a lot of options there. Okay, if you're looking at example 3 here, and again, we won't go through it all, but you could use permutations for this example as well, because if this is your house, let's say, and this is school, you know that you have a whole bunch of different ways that you could go to school. You could go, you know, you could go straight east, all the way over to this intersection here, and then go straight south to school. That's one permutation, okay, of the different routes. Well, you could go straight south first, and then go straight east. That's the second one. You could go almost all the way straight east, and then go all the way down, and then straight east again to get to school. So you see how many different paths you could take, right? You could do all this, okay? And so, of course, there's a way that you can figure this out too. There's many different varieties. So I'm not going to go over the example just here in class, but this is an example of how you could find out how many different routes you could take on a map. So there's that type of question as well. And here's just some examples, right? So anyways, I'll leave that example for you, and we'll get back to the key ideas, and I'll give you your assignment. Just take a minute to read over this. If you have any questions, just let me know in the next minute or so, and I'll give you your assignment. And if any of you are as into the Rubik's Cube as my son is right now, you can take a look at number 19. It's optional. Little square around it, so it's optional.